Here's our first example for simple harmonic motion. So we have a block whose mass m is 680 grams. So our mass would be 0.68 kilograms. Is fastened to a spring whose spring constant K is 65 newtons per meter. The block is pulled a distance of 11 centimeters from its equilibrium position at x equals 0. So x equals 11 centimeters, which is 0.11 meters, from at x equals 0 on a frictionless surface and released from rest at t equals 0. So for part A, we want to know the angular frequency, and period of the resulting motion. So first and foremost, angular frequency, we have a mass and a spring constant K. So we can use that equation. So angular frequency is equal to the square root of K over M. So solving for this, plugging in our numbers, we get K was 65 newtons per meter. Mass is 0.68 kilograms. And so we get angular frequency is equal to about 9.78 radians per second. So that's our angular frequency. We know another equation that relates angular frequency and period. So we know angular frequency is equal to 2 pi over period. So that means period is equal to 2 pi over angular frequency. So 2 pi divided by 9.78 radians per second gives us that the period is equal to 0.64 seconds. And then we know that frequency and period are reciprocals of one another. So we have frequency will equal 1 over period. So 1 over 0.64 seconds equals 1.56 hertz. So that is our frequency, angular frequency, and period of oscillation. Part B, it says, what is the amplitude of the oscillation? So in this case, since we pull this block back to 11 centimeters from the equilibrium position and then let it go on a frictionless surface, the amplitude is just going to be that 11 centimeters. It can't gain any other energy from the energy that we gave it when we pulled it back and then let it go. So therefore, it can't go any farther away from the equilibrium position than that 11 centimeters. So amplitude equals 11 centimeters or 0.11 meter, however you want to put that. Letter C says, what is the maximum speed, the maximum of the oscillating block, and where is the block when it has this speed? So maximum velocity is going to be equal to omega, our angular velocity, times our amplitude of motion. So we get omega was 9.78 radians per second times the amplitude, which is 0.11 meters. So we end up getting a maximum, what the heck? We end up getting a maximum velocity of about 1.08 meters per second. And then this maximum velocity occurs at the equilibrium position. So at equilibrium. Part D says, what is the magnitude A sub m of the maximum acceleration of the block? Maximum acceleration is going to be equal to angular velocity squared times our amplitude. So we get angular velocity 9.78 radians per second squared times the amplitude 0.11 meters. And so we get maximum acceleration is equal to 10.52 meters per second squared. And they don't ask this, but this occurs at the amplitude positions. E, what is the phase constant phi for the motion? Now, since is that phi or phi? I always forget. Since we actually pull it back to a positive equilibrium position, if we kind of graph this motion, and I'm sorry, my graph is very, very shaky, because we let it go, that just looks like a cosine curve. So that means that our phi is actually 0, or phi is actually 0. Phi, I think it's phi. Now we can actually prove this as well because we know that our equation for this is our position as a function of time is equal to amplitude times the cosine of omega times time plus that phase constant. Now here, if we're talking about a time equals 0, we're pulling it back to that x maximum position at time equals 0. So if I leave those in variable form, and then we have cosine times cosine of the quantity 0, because time is equal to 0 there, plus phi. And so we get cosine of phi there, and then we're going to divide both sides by x maximum. So we get x maximum divided by x maximum, which is just 1, is equal to cosine of phi. And then if you take the inverse cosine here, you get phi is equal to 0. Okay, so that's kind of proving it, but the graph also shows you that if you release it from a positive amplitude position, your phase constant will be 0. And then last but not least, part F, what is the displacement function for the spring block system? Our displacement function will be the amplitude, which was at 0.11 meters, times the cosine of the angular velocity, which was 9.78 radians per second, times time. So that is our displacement function as it varies with time.